team representing Iolani School in Honolulu, Hawaii. I'm Kimberly Peterson.
Hi, I'm Arnold Chen. I am Evan Long.
Hi, I'm Courtney Otani.
Hi, and I'm Deanne Ugawa. Our research topic is on wave energy. To address our research purpose, we developed two distinct wave energy conversion devices and tested their efficiencies, feasibility, and applicability in marine environments.
As you can see from this pie chart, fossil fuels are currently the most consumed energy source. In 2010, 80.6% of world energy consumption was from fossil fuels, with only a measly 16.7% coming from renewable energy sources such as wave power. So the main three fossil fuels are coal, petroleum, and natural gas. Fossil fuels are considered non-renewable resources because they take millions and millions of years to form. Therefore, fossil fuels will become more scarce as we continue to use vast amounts of them.
As fossil fuels become more scarce, energy prices will rise. Because fossil fuel prices have continued to rise, more emphasis has been placed on renewable energy resources. And in Hawaii alone, we utilize geothermal energy, which is in use on the Big Island of Hawaii, solar power, and wind energy. However, a new frontier of renewable energy has arrived: wave energy.
Wave energy actually derives its power from wind energy, which in turn derives its power from the uneven heating of the Earth. The uneven heating of the Earth creates temperature gradients across the Earth, which in turn makes areas of denser air and light, hotter air. The light, hotter air tends to float upwards, and in its place comes the cold, denser air, which makes what we call wind.
The size and strength of the waves depend on three factors: the size and duration of the wave, and the distance traversed. A longer, faster wind produces a more energetic wave. Also, the farther a wave travels without dying off, the more energetic it becomes.
Although by definition, a wave cannot be formed without the motion of water molecules, water itself only travels in a circular fashion. This is exhibited, for instance, in a buoy floating in the ocean. The buoy will only float up and down, never with the wave, until the wave breaks near the shoreline. And at that point, the waves do not move in simple harmonic motion. Okay, so to calculate the energy within a wave, we use this equation specifying the total amount of internal energy within a wave propagating fluid, such as seawater. We coupled this result with the powers, experimental powers of our wave energy converting devices to find their respective efficiencies. Okay, so the power of a wave per meter width equals rho, or density, times the gravity squared, times the height of the wave squared, or times the average time of the period divided by 32 pi. To put some numbers out there, a 6-inch or 15-centimeter wave with a period of just about 20 seconds would have a power output of just under 500 watts per unit width of the wave. Although this is about potential energy, in reality, we can only harness a fraction of this amount because of non-conservative forces such as friction on the bearings, and due to the fact that we only address 1 out of the 6 degrees of freedom, which Kimberly will talk about next.
So the ocean contains 6 degrees of freedom, or in other words, the ocean can move in 6 ways. They are heave, sway, surge, pitch, yaw, and roll.
These are some of the various types of wave energy conversion devices that harness the 6 degrees of freedom. This is the oscillating wave surge converter, the point absorber, the overtopper, the oscillating water column, the bobber, and the attenuator.
The two specific wave energy conversion devices we focused on were the Savonius turbine and the heat energy converter.
So the purpose of our project was to test and compare two divergent or different wave energy conversion devices in terms of their efficiencies, feasibility, and applicability in marine environments, such as in the ocean.
Okay, so we started our experiment by first doing our research. So we first went to Ocean IT, an innovative company which showcased the Savonius wave turbine. And we also went to the University of Hawaii at Manoa campus, where Dr. Michelle Tang and Mr. Richard Carter taught us about waves and the engineering of wave energy converting devices. We also listened to a presentation by Mr. Seki from the Hawaiian Electric Company, where he explained how wave energy is feasible as a substantial source of renewable energy.
We designed our wave turbine and our heat energy converter, and then along with that, we made a homemade wave tank out of wood and waterproof protective wrap. And then second, we built our wave turbine and our heat energy converter. We'll show you a movie of one of our tests. So as you can see in this movie, the turbine is spinning from the current produced by the sink, from the water coming from the sink.
We built two models of both of our wave energy conversion devices, one for the ocean testing, which were larger models, and another set for the UH wave tank. And then we went to the ocean to test for voltage and amps, and the wave there ranged from 15 centimeters to 45 centimeters. Then we went to the UH campus and tested the smaller wave energy conversion devices in their wave tank.
So the first wave energy conversion device that we used was the was the turbine, and that harnessed the pitch motion of the waves. The heat motion of the waves, which is the circular motion that the particles of the wave exhibit. And we'll show you a video in a moment, but the turbine only rotates in one direction, even if the water is coming either way, because if it comes this way, it catches the top one, and if it comes the other way, then it catches the bottom one. And the turbine was created using an axle, which was connected to a small motor using sprockets and chain. And the friction was a bigger factor in this device so we used a weaker motor to reduce the friction. And we put bearings in the wood holding the turbine's axle to further reduce the impact of friction and produce more electricity. So here's our video of our ocean test with our turbine. And when it starts up, then you can look at the chain and see the chain moving as the wave comes by, even if you can't see the actual turbine moving. That shows that the turbine was moving when the wave came by and it produced the electricity.
The second wave energy conversion device that we built was the vertical floating device that harnessed the up and down motion of the waves. We utilized a weighted styrofoam that was attached to a chain, which with sprockets also attached to the NXT motor to create our electricity. Because of the way that this device works, it outputs negative and positive voltage. So we created a diode bridge which would allow the voltage to be transferred to only positive, whether it was negative when it originally started moving the motor. Now we will show a video of this device being tested in the ocean. So as you can see, when the wave passes by, it's able to move the styrofoam up and down, which also moves the chain.
For the turbine wave energy conversion device, the peak voltage was 0.3 volts. The peak current was 0.55 amps, and the peak power, using the equation P equals I times V, the output was 0.0165 watts. Using the results from the wave power equation, we found that the turbine's efficiency was approximately 9 times 10 to the negative 4%. The irregular peaks that you see in the graphs are from the waves coming in intermittently.
Okay, for our vertical floater wave energy conversion device, we obtained a peak voltage of about 1.55 volts and a peak current of 0.1 amps, giving a peak power output given by the equation P equals IV, again, to be 0.155 watts. The efficiency was 8.8 times 10 to the negative 3%, which is around 10 times that of the turbine. However, as you can see, both efficiencies were really quite low, and that's because, as I said earlier, of non-conservative forces at play, such as friction on the bearings, and due to the fact that we only addressed 1 out of the 6 degrees of motion.
Okay, so the turbine is feasible on a larger scale. To maximize the power output, it should be in strong currents and with waves with long wavelengths. Also, it's bidirectional, so it only turns in one direction, no matter which way the wave turns, as my partner described before. So the best place to place these would be near shore or in strong, deep water currents, as can be found in the Bay of Fundy in Canada.
So our vertical floater is also feasible on a large scale, and it would be best in places where there's a high amplitude and frequency, and the waves could come in any direction because no matter what direction, the floater will still move up and down. And this device should be placed offshore of a breaking point because that would totally kill our device. And I'm sorry. And places like these, for example, is the North Shore of Oahu.
In order to optimize our two devices, we need further experimentation and research. Larger devices results seem to be better because of the less friction that they have, and we also need optimal sites to test our wave energy conversion devices.
Okay, so for further research, we suggest reducing friction as much as possible and optimizing our designs. Wave energy is, of course, still in its early stages of development, so it needs time and energy, time to be developed.
There are many people we would like to thank for helping us along with our project, and these are just a few. And especially, we would like to thank our mentors, Dr. Mark Lindsay and Dr. Holly Lindsay, for always being there for us and helping us with our entire project.
And here's our bibliography. So if you want to learn more about wave energy conversion devices, you can use some of these resources.
Thank you for your time. Does anyone have any questions?
Is there a way to build a device that optimizes more than one degree of waves?
Yes, there is. There is a wave energy conversion device that's actually in its later stages of development called Polamis. And it's like this long snake thing that has hinges at like a whole bunch of corners, so it can move in any direction. and when it moves, that's what creates energy. So that one is really efficient because it does harness more than 1 degree of freedom.
However, we didn't choose to focus on those because it takes a lot of resources and time, and we weren't sure that we would be able to make it work. So instead, we chose devices that we thought we could actually build on a feasible scale. Any other questions?
You may not know, but when you take a device that can, take advantage of more than 1 degree of motion, are you talking about a 2 times energy increase, or is it, exponentially less?
Sorry, could you rephrase that question?
Basically, with both the devices you built, you got about, 0.3 volts out of each one. Now, if you're going to build a device that took took advantage of 2 degrees of movement, would it give you maybe 0.6 volts, or would it be around 0.5? Would it double every time you increase, the amount of degrees it would take advantage of, or is it exponentially less?
Yeah, so we're not actually sure about that. Yeah, we'll take a look at that.
That'd be interesting to research, so that could also go in our further steps. Any other questions?
Hi, I'm just wondering if you've yet had time to consider the fact that sometimes these wave hubs have an impact on the environment in terms of, you were talking about the North Shore, how that might contrast with or impact your surfing community's accessibility to the North Shore, and sometimes wave turbines can impact local sort of fish stocks as well with the noise that they make. I wonder if you've had time to consider those impacts yet.
Yeah, actually, when we were researching at the beginning, Mr. Seki from the Hawaiian Electric Company told us that wave energy hasn't actually garnered a real start in Hawaii because there are so many local, community protesters who don't want that kind of stuff right offshore. And so that has barred wave energy from really getting its start. So that may be a problem in the future. However, I think that with more research and optimization, they could possibly find a way to make it blend into the environment and over time maybe make less noise so that the fish aren't scared away.
Are there any more questions?
Now could we have the comments from our wonderful commentators?
Well, thank you very much. That's another very clear presentation. And I like the way you worked very well as a team and you clearly practiced that. I was quite tempted to come and join you on my stage, but moving on. I'm from the UK, the very southwest of the UK, and we're surrounded by the sea. And we've only just started to use or to research this sort of technology ourselves. So you're well ahead of us, so well done. One question. In Cornwall, where we're from, seaweed is a big problem. Do you see seaweed impacting your technology?
Probably. There is really no seaweed in Hawaii where we live. So that's not a big impact for us when we were researching, but I could see that as a barrier because especially the turbine would get caught in the seaweed. So maybe further outshore.
Well, if you come to Campbell next for the next science fair, I'll show you plenty of seaweed. Thank you.
Just a couple of, again, quick comments. Number one, focusing on your presentation, I think your teamwork, again, was, as per the first group, I mean, there are certainly challenges when you have a group of 2, and in your case, a group of 5. And those are such important skills to have an opportunity to display. You guys are just perfect. You're just and even how you're answering the questions and responding. It's certainly, you demonstrate that you are a team and that you have collaborated on the whole process. The other aspect is I really like models. I think it's something that's really missing in a lot of research is you're looking at technology, you look at computers to generate all your information without actually creating something. And in our guest speaker yesterday talked about the importance of creating your own model, your own prototype, because you can sense things that you cannot see. A computer can't tell you that. Technology tools can't tell you other than you doing it. So I think those are so brilliant to be able to have an opportunity to do. Two questions then. In the sense of a bobber, what are the, you talk about, I mean, the wave motion and that, but are there optimum wave sizes in the sense of what would be the optimum or a point where it's actually detrimental to the device?
Well, what we found is that our bobber and our turbine worked better in different kinds of waves. We were actually there for a 3-hour period, so we got to experience different kinds of waves that were higher, some that were lower, some that were farther apart. And so we found that our bobber needs time to come back down because of the weight to produce more energy. So a longer wavelength is actually better for our bobber. Oh yeah, and it obviously can't be bigger than this, so yeah.
If you were to take that to a manufactured scale though, would you see the wave, you know, and I'll just use some very generic terms, like so you have nice low cresting waves or you have these big pounding waves. Obviously you're not going to put it on shore because it just wouldn't be efficient, but in the sense of, you know, you might think, oh, the bigger the wave, you know, the greater power output that you'll have. Do you see sort of a limitation? Is there an optimum size? If you were manufacturing this to actually commercialize, what do you feel the ideal conditions would be?
Well, it all depends on where it would be placed, because as you know, different places have different tides and tidal heights and stuff. So it would, I guess it would have to be personalized, sort of, to the area it would be placed in. But I'd say for Oahu, it would be about, well, where the big waves are on Oahu, I would say it'd be about 6 feet high.
And one last question. Here you are, I mean, when you look at feeding into the grid, obviously you're producing power for use, whether it be for residential, commercial, it could be just for something in a navigational device out that, you know, and you could use typically, it's replacing something as such as solar or other conventional forms of energy production. But if you're producing energy, and now you have to get it to a grid which is onshore, what type of challenges would you face, or how would you see that being resolved?
So actually, on Oahu, on one of our marine bases, they actually have had to do it. Like a lot of like initial capital is needed to actually place the cable in the water because it needs to be like special, right? Because it's salt water especially. But once it's there, it's you don't really need that much. It's like you just have to hook it up. So just the initial investment will probably be the biggest, and just trying to get it out there at first. Does that answer that?
Yeah, thanks very much for the presentation. I particularly liked the 6 directions of waves. I could have actually handled a few more seconds of that because I was just, what are they doing? Oh, now I understand. So that was fantastic. Look, I really appreciated your research on using very small waves, capturing the energy of very small movements. You talked a lot about waves produced by wind energy, and just in the question and answer session you put more emphasis on tidal waves produced by tidal movements. water movements as a result of tides?
Actually, our turbine uses the current of the waves, and our bobber needs a high frequency, but a little bit longer wavelength, so it can't be tides and then come back down after like 6 hours, because that wouldn't produce as much energy as a bunch of little oscillating waves. So, for the heat pump, but for the turbine, the tidal waves would be great because it would cause so much current going in. Maybe 30 minutes it would not really have any, and then it would have maybe like 3 hours of coming back out again.
Yeah. The other thing I like about your presentation is that it's appropriate for countries with large populations along big coastlines, and it's certainly relevant to Australia, where most of our population is hugging the coastline. So that was really important. And again, I'd just like to say the confidence that you put into your presentation really made it easy to understand, and thanks very much.
Thank you.
Thank you very much. Now, please welcome our next presenters from